Good morning, everyone. So, in the last class, we have seen the concept of cycle index and before that, Burnside lemma. So, Burnside lemma or cycle index helps us to compute the number of the equivalence classes. For example, in case of two coloring of a square, there are six equivalence classes. But in that equivalence class, if someone asks that how many distinct colorings are there with two black and two white, then we don't have that answer. So in today's class, we will see that detailing using the concept of Polya's formula, that how do we compute the specification related to the colorings. So this concept is known as the pattern inventory. So it is a generating function that tells how many colors of a figure are there using different possible collections of colors. For example, for black white coloring of a square, I have one coloring with all blacks, one with all white, but there are two distinct colorings with two blacks and two whites. So here can be black and black, or diagonally can be black and black, and these two are white. Yes, so it means that this is what 1B3W says, that 3 black and 1 white. So our aim is to compute the coefficient of B4 minus K W raised to the power K in the pattern inventory. And for that, first we need to see how do we compute the pattern inventory. Well, let us consider the following table. So there are 8 symmetries. Then these are the coloring symmetric fixed by. This is cyclic structure. And now you can observe the last column, which helps us to compute the pattern inventory. So this is the inventory with respect to each symmetry. So in the first case, what has happened, that cyclic structure says that there are 4 cycles, each of length 1, and each corner has two choices, black or white. So black or white, black or white, and that's why you will have b plus w raised to the power 4. When I write x4, it is a b c d. It means all four corners should have the same color, and when all have the same colors, then either all four are black or all four are white. That's why I have b4 plus w4. For pi 3, it is acbd. It means these A and C should have the same color, either black or white. Similarly, B, D should have the same color, either black or white. Because of this, for pi 3, I wrote B square plus W square whole square. So I can write down the inventory for each symmetry. Then I add all of them and divide it by 8, because 8 symmetries are there. And that gives us the required pattern inventory. For example, for B4, if you add them, you will get 8b raised to the power 4 divided by 8, which is, there is only one coloring with all blacks. But if you add this, then you will get 16b square w square by 8, which means there are two colorings with two blacks and two whites. Yes, so it means that if I have to compute the pattern inventory, then I must replace each xj by b raised to the power j plus w raised to the power j. If x2 is there, I replace it by b square plus w square. X3 is there, then b cube plus w cube. And if there are three colors, for example black, white and gray, then x2 would be b square plus w square plus g square. So as many colors are there, not a problem, we can always compute the pattern inventory. Yes, so this is what we are doing. We are replacing each xj by b raised to the power j plus w raised to the power j. So this is known as the Polya's enumeration formula, which we have discussed. Now let's see some questions based on Polya's enumeration formula. So determine the pattern inventory for 3 bead necklaces using 2 colors. So we have already discussed in the last class that cycle index would be 3 rotations are there, x1 cube plus 2 x3. Now replace each xj by bj plus wj. So b plus w cube plus 2 times b cube plus w cube. So that gives us the, if you expand it, you will get that there is one coloring with all 3 blacks, one coloring with all 3 whites, one coloring 2 black 1 white, and one coloring 1 black and 2 white. Find the number of 7 bead necklaces using 3 black and 4 white beads. So this is a special case. I don't have to find the pattern inventory, but I have to find the number of distinct colorings, or total number of the distinct colorings with 3 blacks and 4 whites. But for this still I need the pattern inventory. So 7 rotations are there, x1 raised to the power 7 plus 6x7. So if you compute the pattern inventory, it is 1 by 7 b plus w raised to the power 7 plus 6 b7 plus w7. Now I need the coefficient of b cube and w raised to the power 4. So in b7 plus w7 there is no coefficient of b cube w raised to the power 4. And now in this one, b plus w cube, we have discussed it many times. So it is either 7c3 or 7c4, either 3 blacks or 4 whites. So 1 by 7 and 7c3 is the required answer. Compute number of 6 bead distinct necklaces using 3 black, 2 white and 1 grey. Yes, again you need to recall, we have already discussed in case of the hexagon the cycles. From the cycles you can write the cyclic structure and cycle index. So please do write it first and verify that it must be, or it's here. So this is my required cycle index. Now I replace each xi by bi plus wi plus gi. So it is 1 by 12. Then b plus w plus g raised to the power 6 plus 4 b square plus w square plus g square cube plus 2 b cube plus w cube plus g cube square plus 2b6 plus w6 plus g6 plus 3b plus w plus g whole square and b square plus w square plus g square whole square. Yes, now I need the coefficient of b cube, w square and g. Now this term has all the coefficient g square in the higher power, so it does not have b cube, w square, g. Similarly, these two don't have. So there remains only two terms which can have the coefficient. From the first term, it's simple. So 6 factorial divided by 3 factorial, 2 factorial and 1 factorial. Now from the second one, 3 is already there. Now I need only g. So from the first bracket I can have g, from the second bracket I cannot have. So if I take 2bg, and from the next bracket if I take 2b square w square, because this is the only possibility to have b cube w square g. So I would have 3, 2 and 2. So that gives us the coefficient of b cube w square g. If you simplify it, it comes out to be 6, which is the required number of the colorings. So that's all from today's class. This chapter is over. In the next video, we will see an application of Polya's formula to compute the number of 9 non-isomorphic graphs. Thank you.